Hi, everyone. Welcome back to Lecture 5 of MIT Deep Learning. Today, we're going to learn about how we can marry these two very long-standing fields of deep learning, like we've been learning about in this entire course, together with this other field of reinforcement learning. And the combination of the two is going to be the focus of today's lecture. So deep reinforcement learning is quite an amazing intersection of two fields because it moves actually beyond everything that we've seen in the course so far that we've learned, right? So specifically, it moves away from this paradigm of trying to learn on, data that we've seen in the world to make predictions or inferences that mimic those pieces of data. Instead, the movement in reinforcement learning and deep learning together focuses at building this interaction between a model and its environment and its data, right? This is not about just taking a data set that is pre-collected and training a deep learning model on it, but actually having a dynamic environment where the model will interact with that environment in order to learn. And the goal is that we want to ideally try and do this without any supervision, without any human labels, or ideally with as few human labels as possible. Now, this has a lot of obvious implications in the world. Basically, we see applications of this type of technology in everything from autonomy and robotics all the way to gameplay, right? In fact, a lot of the original breakthroughs in deep reinforcement learning have come from gameplay, and we'll see some strategies or some recent works that have really driven forward the field, starting in this field, in this realm as well. Now, I want to start by just setting a little bit of groundwork and laying the groundwork for everything that we're going to see in the rest of the class today, and just taking a step back, first of all, and trying to understand how reinforcement learning fits into this bigger paradigm of all of the different types of learning algorithms that we've seen in the class so far. We've seen two types of things, right? We've seen architectures, right? Lecture 1, we talked about fully connected networks. Lecture 2 was recurrent neural networks. Lecture 3 was convolutional neural networks. These are all architectures. And then we started talking about learning algorithms, supervised learning, unsupervised learning, and today is reinforcement learning. Algorithms are agnostic to architectures, right? So the first algorithm that we saw was supervised learning. Supervised learning focuses on problems like this, where we are given x's and y's. X's are our inputs, y's are desired outputs. And our goal here is to learn a model that, given an x, will learn how to predict a y. From a lot of examples of x's and y's, I can try to learn that mapping concretely. So for example, an analog or an intuitive example here with this apple, right? If I show a lot of pictures of apples to a model, and I say, this is an apple, this is an apple. If I showed a new apple that looks slightly different, it should still be able to recognize that this is yet another apple. Next, we discussed unsupervised learning, right? This was the lecture number 4 that we saw yesterday, where we only have access to the data. We only have access to the x's, but we do not have access to the y's. So there are no labels in unsupervised learning. But now, for example, this apple example is trying to say, okay, if I just show you a lot of these similar things, I don't have to tell you that they are apples, but if I show you another thing in that category, it should be able to detect that, even if you don't know that this is an apple or what an apple means, you should be able to detect similarities in the features just by observing many of these x's. And finally, in today's class, reinforcement learning is the third category of algorithms that we'll be covering in this class. And this is going to focus on moving away from x's and y's. Now we're going to be given what are called pairs between states and actions. Okay? So states are simply the observations that our model will see while it interacts with the environments. And the actions is how it can interact with that environment. It's how it can, make decisions to receive new observations, right? We'll make this more concrete in the next few slides, but really the goal of reinforcement learning is to take all of these state-action pairs, so instead of x-y pairs, just like data and label pairs, now we're going to take state-action pairs, and the goal of reinforcement learning is to learn how to, take actions in this environment such that we see desirable states. right? And we'll talk about how to measure desirability. These are rewards that we'll give to these models over time. But a good example of this is, again, in the apple scenario, we don't have to say, this is an apple or this is not an apple, but just by interacting with these items, a model should be able to learn that it needs to eat apples for nutrition in order to survive, for instance. So today's lecture, we're going to be focusing on this third category of algorithms and seeing how we can build models in this type of world as well. So before we go any further, I want to dig into all of the terminology that I just introduced on the previous slide, right? And I'll just start by introducing the vocabulary, first of all, that we're going to be building on throughout the entire lecture today. So this part is actually a really important part of the lecture because the entire rest of the course will build on this part here. So we're going to start with this piece of the reinforcement learning pipeline on the left-hand side. This is the agent. This is the main actor in the environment. So this is the thing that is taking the decisions. It's taking the actions. So this could be Mario in Super Mario. It could be a drone in a navigation or a delivery setting. In life, we are all the agents, right? We're the ones acting in our environment and making decisions. Then we have the environment. This is simply just the place, the world in which the agent exists and makes its decisions. And of course, the interaction between these two things is that the agent can send actions to the environment, right? Actions correspond to different sets of possible things that this agent could do. So for example, we could imagine a simple two-dimensional world, a two-dimensional environment, where our agent can move in just one of four directions, up, down, left, or right. And you can basically imagine actions living within this discrete space. So you can imagine a very simplified world where you have just four possible actions that you could ever take, up, down, left, or right. Or you can imagine a much more continuous space, right? Like all of our lives, where we have a continuous and infinite amount of actions that can define our future. And finally, this feedback loop closes on the other side as well by the environment sending back observations to the agent, right? Based on an action that the agent takes, the environment will send back and reply, you can think of it like this, with a new observation of how the world has changed by them taking this action. And there's one more step here, is that not only does the environment reply with an observation, the environment also replies with a form of reward signal, right? So this is how it's demonstrating how desirable of a state the agent has now entered into, right? So this is a reward. We'll call this R at time t. And finally, ultimately, what we really care about is not just the reward at one time t, but we're looking at a total reward that this agent is able to accumulate throughout an entire lifetime, right? So the agent will live from, let's say, time 1 all the way to time capital T, and it accumulates rewards over time, which is simply just the sum of all of these rewards from 1 to capital T. But oftentimes, it's actually useful, I want to highlight this, that it's actually useful to not only think about the sum of all rewards, just the aggregate sum of every reward that you accumulate over time, because not all rewards are created equally, right? For example, future rewards are oftentimes much less valuable than current rewards, right? You can imagine this, for example, if I offered to give you $5 today, or $5 in 10 years from today, the $5 is not worth the same amount in that time. Even if without inflation or anything, you would still prefer the $5 today because it's $5 that you could spend today and choose what you can do with it. So oftentimes what we'll think about when we develop these reward functions is not just a total sum of all rewards, but we actually discount future rewards more heavily the farther they are into the future. This enforces some form of basically short-term feedback for the model to be able to prioritize the rewards that come sooner and discourage the rewards that come a bit later into the future. Now, finally, there's this very important function in reinforcement learning called the Q function. So let's look at how the Q function is defined, what it is, and especially putting it into the context of all of these definitions and vocabulary that we've learned so far. So remember this equation, so the reward function, capital R of t, is just going to be the total discounted sum of rewards that happens from time t all the way into the future. So starting from this current time up until the maximum time into the future. Now, the Q function that I mentioned earlier, this is just going to be a function that takes as input two things. It's going to take as input the current state that the agent is in and the action that it will take in this state. And the Q function is just going to return the expected total future reward that this agent will see by taking this action from this current state. So if the agent executes this action, A of t, at time t, given the state that it's currently in, S of t, what is the total future expected reward that this agent could ever receive, by taking this action? Now, the question is, if we are given this, actually magical Q function, I'm not going to tell you how we are given it, but I'm just going to tell you that you are given this Q function. So given a function that if you give it a state and an action pair, it will tell you how much reward that you can expect to receive. Let me ask a question to everyone here. If you had access to this type of function, and I asked you, what action would you pick? Given a current state, what action would you pick? How would you use this Q function to determine your best next action? Right? So you find yourself in a state, and I give you a Q function. Can you use that Q function to determine what is your next best action?
Acts of all future, of all possible actions.
Exactly, yes. So what you would do is ultimately, what you want is to identify what is the best action that you can take in this state. You can use the Q function to basically say, okay, let me evaluate my Q function, as you suggested, over all of these different actions. And for each action, I will compute what is the expected reward that I would receive, and I'll take the maximum of all of those. I'll take the action that gives me back the maximal expected reward based on all of those possible actions. Okay, now remember though, what we really care about is not just observing all of these. We really want to choose the action that maximizes this future reward. So what does that look like? As we said, we can formulate that as the optimal action for any given state is just going to be computed by basically plugging in all of our actions to this Q function, evaluating the Q function across all of these actions, and then picking the action that gives us back the best reward. Okay. Yes?
Question. So I'm thinking of, for example, somebody who is, I'm just trying to see how this is comparable to the human intelligence.
Mm-hmm.
That if you, for example, have a job offer now, or could do a degree for 3 or 4 years and then get a job offer, certain people would think, I'll do the degree now, and then I'll do it, get a better job. Although the better job is
right.
how you kind of calculate it. So is this kind of getting this?
Yes. So the question is basically about how can you not just optimize based on the reward right now, but the reward into the future as well. And that's actually a really good question because, why I want to highlight this is because, remember, the Q function is optimizing over capital R of t, which is the return. And this is not little r of t, which is the reward at time t. Right? So capital R of t, let me go back one slide because this is a really good point. Capital R of t, the relationship between the return and the reward is that the return is the sum, the discounted sum of all future rewards. So this would also account for cases where you take potentially a suboptimal action now for less reward, but this sets you up for a better success in the future. This would be captured in capital R, but would be lost in little r. But remember in Q functions, you actually capture the entire future return that you would expect to take by taking this action. You assume that if you take this action and all optimal future actions after that, what would be the expected return that you could possibly achieve? And this would be how you determine the action. So now in this lecture, what we're going to do is basically focus on 2 different ways that we can learn this, action maker, right, if you will, right? Then there's basically two different ways that I'll tell you about. So number one is ways that we do this by, first of all, trying to get access to this Q function. We already saw that if we had access to the Q function, we could have a good action maker, right? We know how to take actions based on that Q function. The secret is basically you have to find the Q function. This is a magical function, and we'll talk about basically one way to do it is basically by trying to learn the value of that Q function. This is called value learning. So you try to find Q, and then you use Q in exactly the way that we saw, just by taking the argmax over the actions. And then you have another side of learning, which we'll also cover today, which focuses instead of trying to learn Q and then use Q, what if you just directly tried to learn this policy function? Because ultimately your policy function is a function that doesn't get evaluated over all the actions, it just gets evaluated over your states. And this is actually the function that you really care about. You want this function pi of s that takes as input your state and tells you the action. There shouldn't be a need to necessarily say, I want to evaluate my Q function over every action. If I had this pi of s that given a state, it could just directly tell me the action, right? And then how would I use this? I can just sample optimal actions from that policy, right, in order to achieve. We'll talk more about this, but I want to dig into, first of all, the first part of the lecture, which is just going to focus on this first technique that we saw, trying to find a Q function, and then leverage that Q function to find the optimal action. Let's dig into this a little bit more, because I think a lot of the questions will start to get answered as we see an example here. First, I'll introduce this game of Atari on the left, right? Now, for those of you who are not familiar with Atari Breakout, this is a game where the actor is this paddle on the bottom, right? So this is a horizontal paddle that can move only in one of two directions, right? Only left or right, only two actions. And its objective is to basically make sure that it moves in a direction that it can hit this oncoming ball that's approaching it and bounce off of its paddle in order to hit and break off the colored blocks at the top. Now, the objective is basically to break off as many of those blocks at the top before it misses the ball and it passes by. If the ball passes without the paddle hitting it, it loses the game. So it wants to actually basically keep hitting the blocks or keep hitting the ball so it breaks off the blocks. Now, let me present basically a interesting scenario to the audience. So I want to highlight that estimating or even getting intuition about Q functions can be sometimes very difficult for humans. And actually, oftentimes humans are not very good at estimating what are optimal Q functions. So let me give an example here. So here's two different scenarios, state action pairs. There are two different state action pairs. So here's on the A category. This is a category where the ball is coming right to the paddle, and the paddle is going to decide to not move and just hit the ball back and break off some of the colored in the background. And then we'll have another scenario on B, where the ball is actually approaching to the side, and the paddle has to try to move towards it just to catch up to the ball. Does anyone have an idea of which state action pair you would think has a higher Q value if you estimated the Q value for both of these?
I think it would probably be option B, because the reward would be higher, although there is more of a chance, because bouncing to the side would allow it to break more blocks within.
Okay, how about any other answers maybe for A? Yeah, go ahead.
Yeah, because I played this game before.
Yeah.
Yeah. Regardless how old that was, but I think the problem with B is that as you go to the side, this thing it gets kind of slow for some reason. So I think A is.
Okay. Okay. How about we do a show of hands? So people that think A will be better, you can raise your hand. Yeah. And how about B? Okay. Yeah, I'd say probably 60% for B. Okay, so let's take a look at it. So actually, let's take a look at A first, right? And we'll look at actually a policy that implements both of these strategies, just so we can compare them qualitatively, right? So A is basically defined by very conservative actions. It tries to hit the ball straight on to the center of the paddle, right? Now, what does this look like? Here we can see an example of this strategy executed in practice, right? It's very conservative. It usually tries to hit the ball right in the center of the paddle, and it's been trained to do that. But as a result, you see it really starting to break off a lot of the balls also in the center of the game, right? Now, let's take a look at strategy B, where it actually, you'll see something interesting here, that the paddle actually tries to move away from the ball purposely, just so it can come back and hit it at the side and at an angle. Now, why does it do this? It moves away from it. You see it's hiding actually on the left-hand side just so it can come back and hit it from a corner and try to break out the top and get this cheat code, basically, at the top of the game. And it's learned that, there's kind of this cheat code. If it breaks into a corner, it gets like all of these free blocks. Now, this is just one example, right, of trying to demonstrate how, it's oftentimes very difficult to build intuition about what Q functions or Q values are good at in order to determine the best actions that we could take at a particular state. And this is why it requires so many examples to play with these systems in order to encounter just one scenario that looks like that and try to reinforce it as part of learning. So now let's ask ourselves this question, right? How can we train our model to learn a Q function like we just saw on the previous slide, right? Because that's ultimately the objective here is, given the two things that we see on the left, given a state and an action pair. A state is just a current frame of our game, where we currently are at this exact moment, and given an action that we want, let's evaluate how good of an action that is, right? Okay. So now what we can do is create a network in two different forms. We could have a network that takes as input a single action, that we call it multiple times for every action to evaluate its Q value for each of those actions. Or we can have something like on the right-hand side, where we just basically shift the action onto the other side, onto the output side, and basically say, okay, for a single state, I'm going to output the Q value for every possible action, right? These two sides are identical. There's no difference here. The only difference is actually you're changing the parameterization of how you're calling this model. Instead of calling the model n times, where n is the number of actions on the left-hand side, you call the model one time and you get n outputs. So you're basically redefining the model to say, okay, instead of calling the model n times, I'm going to just output n times instead. It's actually the same situation, but what we'll focus on is actually the side on the right, because usually calling the model is very expensive, right? So we want to minimize the number of calls that we have to the model, and we want to say, okay, how many times can we get all of our answers at once, basically, from a single call of the model? Yep.
So the state has to capture not only the state of the paddle, but of the ball and the angle of the ball and where it is. So the state captures a lot more than just where the paddle is. It's capturing
of course
everything.
Yeah. The state captures the environment, right? So the state captures, let's say, it's like an entire picture of the screen. Exactly. Yes. So and basically, this means that what you're trying to do here is that you're trying to train a network that, given a picture of the screen, which is basically exactly what we as humans would see if we played this game, right? What action would result in the highest return? Now, what would happen here if we made an agent that took all of the best actions, right? What would that look like? Well, what this would amount to is basically maximizing the target return for any given state, right? So given a state, we always want to maximize the target return. So given all of these outputs of possible returns, the Q values, we want to maximize those Q values at every possible step, right? Which actually also means that all we really want to do is just take all of the best actions in order to produce that target return. Now, to do this, we can formulate this expected return as if we were going to take all of those best actions, which is just going to be combined, two things combined. It's going to be the initial reward that we get at this exact, instance, RFT, combined with the expected maximum future return that we get in all future steps from this point on. And of course, we also have to apply the discounting factor so that we discount for all of the future returns, because those are not as valuable as our current returns. And this is our target, right? This is our target value that we're trying to optimize for. We also have the predicted value, because we can call our network and ask our network, what did you think the predicted Q value would be? And that's going to be our predicted value. Now, automatically, you should look at these two things, and this should look very similar to what we've seen in other parts of the class, right? We have a predicted value, we have a target value. We can now subtract these two and compute a norm between them, let's say an absolute value or a squared value between these two values. And then this gives us exactly the term that we are describing as the loss, right? This is our loss that we can use for backpropagating, so that on the next step, when we call this Q value, hopefully the prediction is going to be closer to the target return that we would have achieved. And this is exactly the Q loss, right? This is what is known as the Q loss. Let me just summarize this, and then I'll pause for questions before we go into the next section, right? So let's summarize this whole process end to end, right? This is our deep neural network that is our Q network, right? This is going to take as input our state, and it's going to output a Q value for every possible action that this agent could see. We're assuming there are discrete actions here. So there's, let's say, k different actions that the agent could take, and it's going to output k different Q values. These are just k different numbers. So here are the actions that this model could take. Let's say, again, in the game of Breakout, we have 3 actions: left, right, or stay constant. For each of those actions, we can have our model predict the Q value. So let's say, for example, in this given state on the left, the Q value for going left is going to be 20. The Q value for going, staying in the same place is 3. And the Q value for going right is 0. Why is this the case? It's because, as you can see, the ball is traveling to the left and the paddle is already to the right. So if it goes to the right, it knows it's definitely going to not get any more future returns. If it stays in the same, it's also very unlikely that maybe it has a few more time steps to pick up those returns and move to the left, but it's running out of time. Now, with all of those, let's revisit what we talked about earlier in the class. Given all of those Q values, we have 3 numbers now. How do you determine what's the best action to take? You'd look at those 3 numbers. You'd say 20 is the expected return of going left. 3 is the expected return of staying still. And 0 is the expected return of going right. I should go to the left, right? Because I want to maximize my chances at getting future returns. And then I take that action. I actually go to the left. I send that to the game. The game gives me back a new state. Based on my one movement to the left, the state changes of the game, and this whole process repeats over and over again. This exact paradigm, this exact algorithm has been used in practice extensively with many different examples. One example was with Google DeepMind, how they use these networks called Q networks to apply to solve a variety of different types of these breakout Atari games. So basically, on the left-hand side, you can see the state always coming in as input, but now not 3 outputs coming out, but a very wide range of actions that this agent could see could make at any point in time. And you see this very big network in the middle that tries to determine for this action, what are all of the Q values for all of these states. And actually a really, really elegant and really simple, at its core type of algorithm. It's actually amazing how well this works because they tested on so many of these Atari games. And here you can see the performance of those games. Over 50% of the games with this basic method, right? No extra, tips and tricks involved here. This is really just the method that they used. And over 50% of the games surpassed human level performance just with this basic technique. Other games, obviously, on the far right-hand side, you see this tail end that there's plenty of games where these are way more challenging than what a simple technique like this would be able to handle. But still, to me, it's amazing how simple and clean this algorithm is to work at this scale, for this many complex behaviors as well. Okay, one more thing, and then I'll pause for questions on Q-learning. So I want to comment on the downsides, the disadvantages of Q-learning, and this will help motivate the next section in our transition. So number 1, we only talked about these discrete action spaces, right? Discrete action spaces means where your actions are one of n different actions, but you have to choose one of those actions. So this can only model what we've talked about so far. We've only seen how we can model those types of spaces, right? That's obviously a very big disadvantage, and we're going to talk about how we can alleviate that in the future so that we can move more towards these continuous action spaces. That's number one. Number two is going to be on the flexibility of these algorithms. If I gave it the same state twice, it would give me the same answer twice. No matter how many times I gave it the state, I could give the same state 100 times. It would always tell me the next action is the same because this is a deterministic algorithm. There's no stochasticity involved in this algorithm. And we'll also see why this is problematic because it doesn't allow us to deal with stochastic environments as well, right? Our environments are not always deterministic. So we need, policies and action networks that are capable of being stochastic as well. So to address these, basically, these two considerations are going to be the ones that drive forward the next part of the lecture, which will focus on policy learning, not trying to learn the Q network to derive a policy, but directly learning our policy from the model. I'll pause there and just take a couple questions before we go on to the next slide. Yes, you. Sorry.
Someone behind me? Go ahead.
So, 2 points. Firstly, there is an assumption here that all future actions are also the best actions.
Correct.
Next, if the action space is not chess, for example, is this a feasible strategy?
Yes, we'll see some examples of how these will extend beyond to like very large action spaces. It's definitely problematic where you have very large action spaces. I would say in some cases, like for example, chess, right? Chess has, the space of trajectories or space of like solutions is massive, but the space of actions is actually not as massive as one would think, right? At any moment in time, there's a relatively manageable set of possible actions that could be taken. Right? But if you think of like, let's say, even just building out a tree of actions 3 steps in the future, this grows massively, right? Then it's problematic. But remember, your Q network only needs to manage, once, like just given a state right now, actions that are taken at this step, right? So your action space is defined by actions at every step, not actions, jointly over the entire trajectory of all futures. Exactly. So you want constraints. So the question is about, do you have rules on the game imposing on your action spaces? And yes, right, you want to make sure that you only allow for actions when you select an action that are valid actions. Okay, one more question. You've been waiting. Actually, sorry, you've been waiting a long time.
For the rewards, are there scenarios where the reward could be contextual and subjective? So in this case, our example is objective. It's not hitting the number of blocks, but could there be a scenario where we talk about the job? And it depends on how you define that. That
Yes.
can have consequences on how you reward.
Exactly. So the question is about like, how do you define success, basically, right? So this is we didn't touch on this at all, but actually the underlying assumption to all of this is that you have a reward model that is calibrated with what you believe is true reward, right? So if something says that, okay, you receive a reward of, whatever, of 100 points, it actually calibrates to 100 units of reward for that individual, right? Defining that calibration metric is a very difficult problem. We completely glanced over this, right? But who defines this is the game maker, right? It is the person designing the game. This is not a learned thing, right? Whoever sets up the game defines what the rewards are because it's part of the rules of the game. Excellent. Okay, so for the sake of time, let's keep pushing forward. And I'll zoom back out to these 2 parts of the reinforcement learning algorithms that we've been talking about so far. So far, we've only talked on this left side, right? We're focusing on cases where we want to learn the Q function, use that Q function to determine the optimal action by picking the maximum, the action that gives us the maximum future Q, or the maximum future return. Now let's focus on policy learning algorithms, which don't aim to learn this intermediate Q function. They aim to directly learn the policy. So the policy is, again, this function that takes as input the state, such that if you sample from this policy function, you directly get an action. It does not need to necessarily be an optimal action, but it should be one of the good actions. If you sample from it enough, it should be on expectation the best action. We'll talk about this more detail in this next section. So one quick recap now. So what did we just see with Q networks? We're going to build off of all of that to go into the policy networks as well. So what did we just see? Deep Q networks take as input the state, they output all of the Q values for all of the actions, and we pick the argmax over those actions. For policy networks, the only difference that we're going to make now is that we're going to directly output not the Q value, but for each of those actions, we're going to output a probability that that action would have been the best action from our Q value. Okay, so let's break that down a little bit more. So let's go back to this example with Atari. Instead of outputting the Q value for each of those actions, I'm now going to output this probability score. Okay, so the probability that me going to the left-hand side, given this state, we'll see when we evaluate our policy network, is 0.9. With 90% probability, we believe, given this network, that the left action is the best action. With 10% probability, we see that staying still is probably the best action. And with 0% probability, we see that going right is the best action. So we've changed the definition of kind of what is the output. Why do we do this? Well, it's because if we have a probability function over our output space, it means that now we can pick our best action not just by taking the maximum of these numbers, but we can sample from that probability distribution, right? In order to determine what is our next action to take, we can take all of those probabilities and sample from them so that 90% of the time we would get the action going left, but 10% of the time we would still get this action staying still. We have to enforce, of course, that because we're now dealing with probabilities, we have more constraints on the model's output, right? So now, number one, the biggest constraint is that probabilities have to add up to 1. So we have to enforce that the output of our model respects that constraint. First of all, we can do this, for example, with softmax. Basically, we're dealing with a classification problem almost at this point, right? We're trying to classify, given a state, what is the optimal next action that we want to take from this state. Now, I want to open up a little bit for some ideas. Maybe we can get like 2 people in the room can tell me what are the main advantages that you see with this formulation so far, even without going into much depth. Yes?
With this approach, you would take that 0.1% time sometimes.
Yeah.
The other approach you
Good. Yeah. So sometimes we would get some exploration, right, of maybe less, optimal or less maximal actions. Yep.
Because you're sampling, you could also see which direction you're going to go based on this action. Like, what is the next action? Is that a positive or a negative?
Right. So yeah, it gets back at a similar point, right? So exploration as well. Yep. One more.
You reduce time complexity because now you are not computing each of the.
Well, you'd still have to compute each of them because it's still you're outputting all of the probabilities, right? So the time complexity of this network is still going to be the same. Let's see. Try and call in someone new. Yes.
We no longer have to wait for the evaluation like we have to use earlier, right? So evaluation time gets kind of reduced, I guess.
Yeah. Go ahead.
The main advantage is here is where obtaining the Q function might be very hard to calculate and estimate over the time period that is interested.
Exactly. Yeah. Exactly. So like the point is that you're getting a more direct function to the thing that you're desiring, right? Which is exactly the point. And we'll see actually, we'll make that more concrete. It'll be more clear like why you would want to do that in a second. So one advantage here, actually tied, if you combine all of those pieces together, actually, an implicit thing that hasn't been said is that you can now deal with both discrete and continuous actions, right? Before we could only deal with discrete actions because it only allowed us to estimate Q values for a finite set of different actions. How could we do this for continuous actions as well? So for example, here's a discrete action space, left, right, or stay in the middle. And we can see that basically, okay, we can have a probability of doing each of those actions is the best action. That's a probability over a discrete space. But what if, for example, we wanted to change this into a continuous space? Like instead of saying left, right, or stay, if I said how fast to the left or how fast to the right do I want to move? Now all of a sudden we're not having a 3 different actions. This is now an infinite action space that can be any number on this real number line on the x-axis. How could we generalize this approach to deal with that? Q networks would not be able to do this, but with policy networks we can do this because now we can actually model a continuous probability function over the output and say, okay, for this probability mass, can we estimate this with our model? And then can we sample from that mass to produce our best action? So now what we want to say is, okay, the probability, or let me say it like this. The best action that I should take at any point in time is just going to be a sample from this estimated probability distribution that I can predict with my network. So let's take a look at how we could actually model these continuous action spaces with a policy network type of method. So instead of predicting the probability for each of those 3 different classes like we saw before, or let me say instead of predicting the probability for every possible action that could exist, which of course we cannot do this for an infinite number of actions. Even if we just have one number like the speed, it's an infinite number of speeds that this model could take. So we can't do that already. We've thrown that approach out. Now, how would we do this for output distributions that are basically having an infinite number of actions? Well, we could do this by parameterizing our action space by a distribution, right? So a distribution, like you can see here, this is a Gaussian distribution. How many numbers do you need to generate a Gaussian distribution? Any Gaussian distribution? Yep, just 2 numbers. So 2 numbers would describe this entire probability mass, right? You need a mean. This tells you at the center of your Gaussian, and you also need a variance, which tells you the width or the spread of the Gaussian. So now you just have a prediction of, instead of an infinite number of actions, you just predict 2 numbers. You predict a mean and you predict a variance, and this tells you your probability score for every possible speed that this model could take. So if we want to then sample, and say, okay, what is the speed that my model should act on? Well, I could just look at my mean and my variance, and I could sample from that distribution, and that distribution will tell me exactly, right, that my optimal, mean and variance would be at this point, right, close to the mean, but maybe with some spread. And of course, again, just like before, we have to have this constraint of probabilities summing to 1, right, which we can do because we actually explicitly parameterize our model using this Gaussian formulation. Okay, so now let's look at, let's tie all of this together with a concrete example of policy gradients in practice, right? Let's think of how we could take this method and use it to train an autonomous vehicle in a kind of simplified environment using reinforcement learning and this policy method, right? So here the agent is going to be a vehicle that we want to navigate in a world. Actually, let's simplify it even further and just say not navigate, let's just say stay in your lane and don't crash. This is the criteria. The environment is going to be where it is on the lane, right? How far from the center line it is and so on, and its movement in that world. Its actions that it can take will be just the steering wheel angle, right? At any moment in time, it can execute a steering wheel angle. Steering wheel angles are continuous, right? You could be any angle within a wide range of angles. And finally, the reward, let's keep it simple. You won't get a reward on every single time step. You'll just get a penalty if you crash, and you want to maximize the time before you crash. This is the reward. So okay, let's pull all of this together and let's see how we can train this network in this context. So we're going to start by firstly initializing our agent. We initialize the car in this environment, and we're going to run our policy. So at every moment, at every step, how did we run this policy? At every step, we computed our policy probabilities. We sampled from those probabilities to compute the action that the car thinks that it should execute at that time. And then it executes that action, and it repeats this in a loop. Of course, in the beginning, it was never trained, so the policies are really bad. The probabilities are very uncorrelated with what is safe, so it travels very, doesn't travel very far, and it ultimately crashes. What we're going to do, though, is for each one of those steps, we will record every state and every action pair that it executed and it saw. And as well, we will also record the rewards that it saw in each one of those stages as well. So at each one of those steps, we will have a triplet of 3 numbers, a state, an action, and a reward pair. And then finally, what we'll do is we'll go back to our policy network, and we will just do 2 things. We will decrease the probability of every action that happened in the low reward parts of this sequence, which will be the things close to the crash. Right? So roughly we'll have 2 parts of this sequence, the parts close to the crash and the parts far from the crash. The parts close to the crash, we will decrease the probability of everything that happened close to that part, and we will increase the probability of repeating all the actions that happened and everything far away from that crash. Then we will repeat this entire loop again from scratch. We will reinitialize the agent, we will start it, rerun the policy, we will re-record new state action reward triplets, and again, we will do the same thing. Right? We will decrease the probability of the things that came later and increase the probability of things that came sooner. Don't get caught up on later versus sooner. The point is actually we're decreasing the probability of the penalized actions and we're increasing the probability of the good actions. The fact that the good actions were actually earlier and the bad actions were later is just a consequence of this particular example. It doesn't necessarily need to be the case. Now we keep repeating this over and over again, and eventually you'll learn that the agent can keep learning from all of its mistakes, keep increasing the things that went good and decrease the things that went bad, and eventually it starts to kind of follow these lanes without crashing. Now, this is really amazing because number one, we never showed this model any information about the environment. We never taught it the rules of driving, or that it has to stay in its lanes. We only gave it an extremely sparse reward signal that we penalized it when it crashed, when it exited its lanes. We never told it anything explicit. We never gave it any examples of humans driving in order for it to learn this task. But it's able to learn this task just by interacting with the environment and receiving those reward signals iteratively. Now, I think the nuance here, of course, is in this part of the algorithm, right? So these last 2 steps especially, this is where the nuance really starts to drive home. How did we increase the probability of the good things happening, and how do we decrease the probability of the bad things happening? Because this is how we trained our model. Step 4 and 5 is the training and the backpropagation that we haven't talked about. Everything else is actually just forward propagation through our network and collecting information. So how do we do this? Let's actually walk through this part. And there's 2 parts to any training. There's the loss function, and then it's how you backpropagate after this. So we have to understand what is our loss for this type of step 4 and 5 that we see here. So the loss consists of 2 terms, right? Number 1 is going to be the log likelihood, right, of selecting an action based on what was currently chosen. And then second, we're going to multiply this by our discounted return, R. Okay, so let's pause on this a little bit and let's step through it step by step, right? So first of all, this is the first part. This is the log likelihood of seeing that action, of selecting the action that was selected. And then part 2 is the reward, the return, right? Let's assume that we got a lot of reward for an action that had high likelihood, okay? This loss would be very large because you multiply 2 large numbers together, and you would negate it, note the negative sign in the beginning, which would mean that you have a very negative loss in the end. That's a very desirable state, right? You did a high likelihood action for something that returned a lot of reward. So you want to keep doing that. That was really good. Let's take the opposite case. Let's say that you had a reward that was very low for an action that was very high probability. So you took an action that looked really confident to you, but it resulted in a really bad reward. You multiply those two numbers together, you're going to have a much smaller number. You negate it, it's going to be a bigger number. Okay. When you plug all of this together, you get this loss function that now you can backpropagate through, right? You plug those two numbers in, you compute that loss, and you can backpropagate to update your network in order to find, and to update the likelihoods, because ultimately, let's say in that case where you had a high likelihood action that resulted in a bad reward, the next time you run that network, you don't want the likelihood to be high anymore. The next time you run it, you want the backpropagation signal to say, okay, I wanted to lower this because now the loss told me that I should be penalized. So when I backpropagate, I'm going to update all my weights, so the likelihood on the next time is going to be much smaller. And that's exactly what we do. And if you actually plug this in, you get this equation, which looks like this. This is a gradient descent equation. Hopefully it's familiar to everyone. But the key point here is this policy gradient, right? So the reason why this algorithm is called policy gradients is because you're computing the gradient over your policy, which is this likelihood function, right? This is just where the name comes from. Now, I want to go back to this algorithm, the pseudocode for this algorithm, and talk about this a little bit, not in this toy world, synthetic world that we saw in the 2D driving example, but what if we wanted to do RL in the real world, right? How would this story change? What would we need to consider? How would we have to deal with some of the shortcomings here? So I want to actually open this as a question, right? What does everybody in the audience think is the limitation, right? Which step here is going to be the problem if we wanted to do exactly the same process that we saw in the 2D driving world, if we want to do that in real driving, right? Which step of the 5 steps here is going to be the one that really is not so good?
There are many more states than what you will see. You're not going to see all the states.
Yes, true. But depending on your simulator, it could also be true, right? You could have a very big simulator with a bunch of states as well, and it could also have a wide action space. What else? Yep.
You want to do the kernel policy determination, you want to do it earlier than that, because in this case there are consequences.
Exactly. Yeah. Exactly. So yeah, step 2. Yeah, this is the problem, because termination is, as the name implies, it's not a good. You don't want to run a policy until termination, because in the real world this is like basically you don't want to reach termination in the real world. You can do this in simulation, it's not a problem, but in the real world, basically in order to do everything that we talked about so far, we need to run until termination. So this is not going to work out so well. Now, of course, people have tried to solve this by really advancing photorealism and simulation to the point where termination is safe. You don't need to run to termination and deal with consequences in the real world. So actually, one really cool result that we created here at MIT was, the lab that actually I'm part of, just upstairs. We do a lot of work with autonomy and robotics, and we created this extremely photorealistic simulator. This was now a few years ago, but you can see actually images from this simulation engine. These are videos of an autonomous vehicle running the same reinforcement learning policy that you just saw on the previous slide through this simulator with extremely photorealistic scenes and actually training end-to-end entirely in simulation in a way that we can then deploy this model directly into reality as well. And we did that actually. So this was the model that's just located one level below where you're sitting today. In the garage of this building, we have a car that we took to our test track, trained it in exactly the same way with the algorithms that you learned about in today's class, and then deployed it in real-world roads, right, directly from simulation, using the same algorithms, but done in a very safe way because it's all with photorealism, right, and able to directly translate into reality. So now I think we've covered a really strong foundation of both Q-learning as well as policy learning, so that you can understand, given actions and environments, or agents and environments, how we can optimize our agents to perform actions in those environments. But I think one really exciting thing that when I was learning about all of these algorithms was was really intriguing to me was trying to understand how we could translate, similar to the autonomy and the robotics situations, how we could translate a lot of these from, not just the toy cases that a lot of reinforcement learning literature has covered for many decades, into some of the real world use cases. So one of the big advances and the breakthroughs of reinforcement learning came several years ago with the game of Go, right? So reinforcement learning agents were put to the test on this game because Go is a game with extremely large action spaces and very complex behaviors. At the time, these reinforcement learning agents were put to the test against human grandmasters, and that brought a lot of really exciting results. The game of Go is really interesting, and maybe I'll just give a quick background very quick to the game. So this is a 19 by 19 grid. It's a two-dimensional game, and you can either hold white pieces or black pieces. The thing that's special about Go is that, what do you want to do? You want to just occupy more of the board than your opponent. So you want to take up more board pieces than your opponent. Though the grid and the game are actually relatively simple. This is a two-dimensional world, 2 players, black or white. Sounds actually really simple, but the thing is that because of the 19 by 19, there's an explosion of possible actions that you can take, and even more than that, it's the explosion of possible steps of actions that you can take if you go out a few steps into the future. So in fact, in the full-size game of Go, there are a greater number of legal board positions than atoms in the entire universe, right? So the objective here is to train an AI that can not just interpret those board positions, but given a board position, find an optimal policy. What's a probability of every action being the optimal action that it could take in order to beat those current or past world champions of the game, right? So how did Google DeepMind solve this? So they developed actually a very similar pipeline to the ones that you learned about today. It still is, not that different, actually. It's very hard to beat these algorithms. Is basically the idea, starting from the left-hand side, is going to be first, train this neural network that watches human Go players and learns, given a board state, an optimal action for that board state. Just predict the next state. Right? This is not reinforcement learning. This is supervised learning. So given examples of state 1 and the next state that a human would take, predict the next state. Supervised learning only. But then use that network as a beginning network to train your reinforcement learning network. So now you should have kind of a early version of a beginning Go player. Just by watching a lot of these Go games that have occurred, you can learn some of the dynamics, some of the behaviors that are happening, and you can predict the next state in some way. But then use reinforcement learning to play against itself and get rewards based on when it wins and when it doesn't win, so it can actually continuously improve. Not just be limited based on what the human games were being shown, but actually extract more meaningful feedback and more meaningful signal through its own reinforcement and its own reward signals. Now, one of the tricks that really brought this idea to the next level was this third layer, right? Was the ability to say, okay, let's not just do the learning with ourselves, right? Playing against ourselves and trying to extract that reward, but actually try to, at every stage, evaluate what the value or what the score at that point in the board was. Because you can imagine Go, like chess, for example, is a game where the signal is not seen until the very end, right? And if you only have one signal at the very, very end of the game, it's very hard to say, okay, did this one move that I make much earlier in the game, was that the move that caused me to lose this game or win this game? So the signal, this is another way to say, the signal is very sparse. You only have one signal, and it has to sparsely travel all the way back through time. And the challenge here is that you don't only want this sparse signal. The trick that was employed here is saying, okay, can I create a value for every possible board state that could have? So as I see board states, can I evaluate how good of a state that was at this time, already at this time? And having a good measure, and actually human players do this in chess, for example, they can look at a board without seeing any past or any future moves, and I can say this is a good state, this is a bad state. Like, which side would I rather be on? If I just look at this board and I can pick up this board, would I rather be black or white? And that's basically this question here. And you can plug in all of these pieces together to basically say, okay, I'm going to train this end to end and self-optimize this reward model. Now, the one limitation, actually, the one thing people really didn't like was that first stage where you had to show it the human games first, right? Because this actually seems very unnecessary. You shouldn't have to do this. And in fact, you don't have to do this. So you could start, and this is what was later shown, is that you could start from scratch, self-play from scratch using both reinforcement learning from playing against yourself with the AI against the AI, and having this value understanding of every board state in the game, to not even pre-train these systems based on the human feedback. Okay, I will summarize all of this very briefly. So we covered a lot in today's lecture. We covered a lot of the foundations, a lot of the terminology and the background to reinforcement learning. We brought that up and we basically covered two different sides of reinforcement learning, both the Q learning side as well as the policy learning side. And then we transitioned to cover some of the applications of how these systems are used in a variety of different, both autonomy applications, but also gameplay applications. There's a ton of different areas that people are covering here. That's it for the reinforcement learning part. We will transition to Ava's lecture for the day. And maybe just while we do the transition, I'll highlight that tomorrow we're doing t-shirts and guest lectures. I'll keep this up on the screen while we do the transition, just for some information. But yeah, please come back tomorrow, because I think tomorrow's lectures are going to be some of the newest content that we're showing today, and it's going to be brought by some of our leading industry speakers. So really looking forward to tomorrow's lecture, and also giving you guys some course swag as well. Okay, thank you.
Thank you.